The Voyager 1 space probe from the National Aeronautics and Space Administration, NASA, has re-established contact with Earth. The probe is 24 billion kilometers away from the planet and was constructed by humans at the farthest point in space. The team on the ground contacted it using a radio transmitter that hadn't been used since 1981. The team was able to determine the source of the problem thanks to this temporary connection. At the moment, Voyager 1 is sending faint signals back to Earth while traveling through interstellar space at a speed of 61,000 kilometers per hour. In recent times, it has faced multiple technological issues. Questions about Voyager 1's ability to complete its mission have been raised in light of recent difficulties, the most recent being this transmitter malfunction. While sending a regular heat instruction to the space probe, the transmitter started acting up. There are 3 RTGs, or radioisotope thermoelectric generators, that keep Voyager 1 running. These power plants harness the thermal energy released during the natural decay of plutonium-238 to create energy. After over half a century, this system is still going strong. However, performance degrades as plutonium slowly decays, with each RTG losing around 4 watts of power on average. This means engineers have to carefully select how to best employ the remaining power as Voyager 1 travels through interstellar space. The spacecraft also encounters high-energy cosmic radiation, which over time can harm its electronics. For instance, electrical circuits can lose power when high-energy particles damage transistors and cause minor mistakes in semiconductors. Slowly but surely, these issues pile up, and eventually systems may stop working altogether or perform poorly. Keeping the spacecraft operable requires careful monitoring of radiation damage. To counteract this, NASA engineers may occasionally instruct the spacecraft to turn on its heaters. These heaters can warm portions of Voyager 1 vulnerable to radiation. When materials are heated, they can regain part of their original functionality. For example, heating semiconductors can realign radiation-disturbed atoms, correcting minute faults. This process, known as tempering, restores some of the electrical characteristics of the materials, improving the reliability of electronics. Another source of trouble is the frigid temperatures of space. Extremely cold temperatures increase electrical resistance in circuits, making the flow of electricity more difficult. The heaters lower resistance, boost system performance, and prevent the spacecraft from being overstressed by heating these components. This clever application of heat stabilizes Voyager 1 and prolongs its mission even after decades in the harsh space environment. Engineers routinely ordered the activation of the ship's heater on October 16. Unexpectedly, commands to activate Voyager 1's heating were transmitted over the Deep Space Network (DSN) from the Jet Propulsion Laboratory in California, which is part of NASA. Spacecraft like Voyager 1, its identical twin Voyager 2, and others in the solar system communicate through the DSN, a network of massive radio antennas spread throughout the globe. After receiving a directive, it takes Voyager 1 about 23 hours for the command to travel over 24 billion kilometers and reach the spacecraft. Once the command is received, Voyager 1 follows the instructions and transmits technical data back to confirm its status and activities. This gives Earth-based engineers nearly 2 days to issue an order and receive a response. Everything is done slowly yet precisely. On October 16, NASA engineers routinely ordered Voyager 1's heating to be turned on. However, an unexpected event occurred. Despite having sufficient energy to run the heater, the command disabled the spacecraft's fault protection mechanism, which is designed to preserve power by preventing unnecessary shutdowns of essential systems when power consumption exceeds expectations. On October 18, Mission Control noticed unusual behavior in Voyager 1's signal. By October 19, it was clear that the data transmission rate had been altered by the fault protection mechanism. The team believes that Voyager 1's main X-band transmitter was turned off due to the fault prevention system being activated twice. The X and S bands are the primary means of communication between Voyager 1 and Earth, like separate but complementary channels on a radio or walkie-talkie. Early in its mission, Voyager primarily used the S-band, a lower channel operating at approximately 2 GHz. This channel is similar to a dependable older radio channel suitable for simple communications, although it is not ideal for transmitting large amounts of data. Despite this limitation, the S-band has good long-range capabilities, much like a sluggish but reliable internet connection. Switching to the X-band was akin to upgrading from a basic radio to a high-speed internet connection. This transmitter has been operating for decades to maintain communication with Earth. Despite the challenges, engineers continue to adapt and monitor the probe's operations to keep it functional as it ventures deeper into space. In a dependable range of 8 to 12 GHz, Voyager 1 shifted to its backup S-band transmitter due to the X-band transmitter being down. The S-band transmitter uses less power and transmits weaker messages. The fact that the S-band transmitter had been in use since 1981 made an already challenging situation much worse. Due to the immense distance from Earth, the team was unsure if it would receive the feeble S-band signal from Voyager 1. However, the spacecraft once again shocked them. An essential link to the spacecraft was briefly restored when the signal was located and received by the Deep Space Network, thanks to its cutting-edge technology. The engineers proceeded cautiously. They decided to wait before attempting to activate the X-band transmitter until they had a complete understanding of what triggered the spacecraft's fault protection mechanism. Given the vast distance from Voyager, each signal sent and received takes about 2 days to travel and return, making problem detection a process that could take weeks. A computer glitch that had disrupted scientific data for months was also corrected. The team found a solution by ingeniously separating the corrupted code into smaller pieces and storing them in various locations within the space probe's flight data subsystem. These creative steps demonstrated the team's determination to continue this groundbreaking mission after nearly half a century in orbit. Voyager 1 isn't the only spacecraft to implement energy-saving tactics by turning off unused systems. Voyager 2, its sibling spacecraft, has also faced similar challenges. Engineers from NASA recently turned off Voyager 2's plasma research instrument to conserve power, which is becoming increasingly scarce as the spacecraft's energy source diminishes. Just 2 weeks before Voyager 1 set out to investigate the outer planets and interstellar space with its 10 scientific instruments, Voyager 2 began its mission on August 20, 1977. Jupiter, Saturn, Uranus, and Neptune, the 4 largest planets in our solar system, were explored by Voyager 2, making it the only spacecraft to reach all 4. Nevertheless, Voyager 2's power source gradually weakened, similar to Voyager 1. Engineers had to prioritize which instruments to keep operational as electricity continued to drain. Over the years, 6 of Voyager 2's 10 instruments were turned off to conserve power. The 7th instrument was incorporated in 2024. Among the crucial scientific tools carried by Voyager 2 was the Plasma Science (PLS) instrument, designed to gauge plasma's velocity, density, and temperature. Voyager 2 departed the heliosphere and entered interstellar space in 2018, as confirmed by the PLS. The heliosphere, created by the solar wind, is a massive bubble of charged particles that travel outward from the Sun, acting as a shield to protect our solar system from cosmic radiation. The investigation of solar wind was greatly assisted by Voyager 2's plasma research instrument. By analyzing its characteristics, it pinpointed the point at which the solar wind weakens, signaling the spacecraft's approach to interstellar space. Voyager 2 provided the first direct readings of plasma density outside the heliosphere, marking a significant scientific milestone. These findings have deepened our understanding of cosmic radiation and magnetic fields in regions previously inaccessible to direct observation. However, maintaining communication will become increasingly challenging as Voyager 1 continues its journey farther from Earth. Each signal received will endure a lengthier journey and become considerably weaker. Despite these challenges, at least one scientific instrument on each spacecraft is expected to continue transmitting data from interstellar space until around 2030. After that, Voyager 1 and Voyager 2 will continue their silent journey through interstellar space, though they will no longer be able to transmit data. Each Voyager probe carries a golden record containing Earth-based audio, video, and message data, a symbolic time capsule intended to share humanity's story with any extraterrestrial civilizations encountered in the future. Even when the scientific missions of the Voyagers conclude, their legacy will endure. These probes persist in pushing the boundaries of human understanding and exploration, serving as remarkable emblems of ingenuity and our relentless quest to explore the universe.